Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual ferment of the early 20th century, few scientific revolutions have rivaled the bewildering pace and profound conceptual upheaval of quantum theory. The period following 1925 was a whirlwind of breathtaking discovery, yielding Werner Heisenberg's matrix mechanics and Erwin Schrödinger's wave mechanics, two distinct and seemingly irreconcilable mathematical formalisms for describing the subatomic world. While physicists celebrated these powerful new tools, the underlying logical and mathematical structure of the theory remained obscure, a patchwork of brilliant intuitions, ad hoc rules, and computational recipes that worked with unnerving success. The situation cried out for Euclid, an architect who could survey this chaotic landscape of new physics and erect upon it a single, logically coherent, and mathematically rigorous edifice. That architect was John von Neumann, and his 1933 masterpiece, Mathematical Foundations of Quantum Mechanics, constituted a singular act of intellectual consolidation that reshaped the very grammar of theoretical physics. This work provided more than a new language. It supplied a conceptual framework so powerful and pervasive that its axioms and structures are now almost inseparable from the physical reality they describe. The primary achievement of von Neumann's treatise was the definitive identification of the abstract, infinite-dimensional complex Hilbert space as the proper mathematical arena for all of quantum mechanics. Before his intervention, physicists operated with two different mathematical toolkits. The proponents of matrix mechanics worked with infinite matrices and their algebraic manipulation, a method that excelled in describing discrete quantum jumps but felt abstract and disconnected from physical intuition. Wave mechanics, by contrast, utilized the familiar language of differential equations, describing quantum states as continuous wave functions evolving in space and time. Paul Dirac, in his own transformative work, had begun to build a bridge between them with his bracket notation and transformation theory, yet his methods, while powerful, possessed a level of mathematical informality that troubled purists. Von Neumann, steeped in the formalist tradition of David Hilbert's school at Göttingen, sought to place the entire theory on an unassailably rigorous axiomatic footing. He demonstrated that the two pictures, matrix and wave mechanics, were merely two different representations, two specific coordinate systems within the same underlying abstract vectors. Within this framework, von Neumann established the canonical mapping between physical concepts and mathematical objects. A physical state of a quantum system corresponds to a normalized vector, or more accurately, a ray in Hilbert's space. Physical observables, quantities like position, momentum, and energy, correspond to self-adjoint, or Hermitian, linear operators acting on the vectors in that space. The possible outcomes of a measurement of an observable are the eigenvalues of its corresponding operator. This formulation provided an elegant explanation for the quantization of energy and other quantities. The discrete spectrum of eigenvalues for certain operators naturally yielded discrete, quantized measurement results. The probabilistic nature of the theory, first postulated by Max Born, also found a precise geometric home. The probability of measuring a particular eigenvalue is given by the square of the magnitude of the projection of the state vector onto the corresponding eigenvector. The expectation value of an observable for a system in a given state is calculated through the inner product of the state vector with the vector that results from the action of the operator on that state vector, a formulation that elegantly encapsulated the statistical heart of quantum phenomena. This axiomatic structure transformed quantum theory from a collection of computational rules into a complete and self-consistent mathematical discipline. One of the most profound and philosophically charged contributions of the book is its sharp delineation of two fundamentally different processes governing the evolution of a quantum system. The first process describes the evolution of an isolated system. This evolution is continuous, deterministic, and reversible, governed by the Schrödinger equation. In the Hilbert space picture, this corresponds to a smooth, unitary transformation of the state vector, akin to a continuous rotation that preserves its length and the angles between all vectors. This predictable evolution persists as long as the system remains undisturbed. The second process, however, is discontinuous, probabilistic, and irreversible. This occurs during the act of measurement. When an observable is measured, the state vector instantaneously and unpredictably jumps, or collapses, from its initial superposition into one of the eigenvectors of the measured operator. This is the famous projection postulate. The choice of which eigenvector it collapses to is fundamentally probabilistic, with the probabilities dictated by the geometry of the initial state. This dualistic description of reality, a smooth deterministic evolution punctuated by abrupt probabilistic collapses, introduced a deep schism into the heart of physics. It elevated the role of measurement and the observer in a way that remains a source of intense debate, giving rise to the seemingly intractable measurement problem that has haunted the foundations of physics ever since. Von Neumann provided no resolution to this puzzle, but he gave it its clearest and most unavoidable mathematical expression. Beyond formalizing the role of vectors for pure states, von Neumann introduced a far more general object for describing quantum systems, the statistical operator, now universally known as the density matrix. He recognized that state vectors were sufficient only for describing systems in a pure state, meaning a state of maximal knowledge where the system's wave function is completely known. In many physical situations, particularly in statistical mechanics or when dealing with subsystems of entangled pairs, the system exists in a mixed state, representing a statistical ensemble of different pure states. A classical coin, for instance, has a 50% probability of being heads and a 50% probability of being tails. It is in one definite state. We are merely ignorant of which one. A mixed quantum state is a deeper, more entangled kind of uncertainty. To handle this, von Neumann introduced the density operator, ρ, which is a positive semi-definite, self-adjoint operator with a trace equal to 1. For a pure state psi, the density operator is simply the projection operator onto that state. For a mixed state, it is a weighted sum of such projection operators. This powerful generalization allowed the tools of quantum mechanics to be applied to thermodynamics and statistical physics, creating a field of quantum statistical mechanics. Its true significance, however, would become even more apparent decades later with the dawn of quantum information theory, where the density matrix is the indispensable tool for quantifying entanglement, decoherence, and the informational content of quantum systems. This particular contribution showcases von Neumann's extraordinary foresight, developing a mathematical object whose full power would await the invention of entirely new fields of inquiry. The book is also famous for what appeared to be a definitive refutation of hidden variable theories. A persistent question, championed by figures like Albert Einstein, was whether the probabilistic nature of quantum mechanics was a fundamental feature of reality or simply a reflection of our ignorance of a deeper, deterministic layer of hidden variables. In a brief but dense chapter, von Neumann presented a mathematical proof demonstrating the impossibility of supplementing the quantum formalism with such variables to restore determinism. The proof rested on a set of seemingly plausible assumptions about how these hypothetical hidden variables would behave. One crucial assumption was that the expectation value of a sum of observables must equal the sum of their individual expectation values, a property that holds for compatible observables in quantum mechanics. Von Neumann assumed this linearity would extend to all observables, including those that are incompatible, like position and momentum. Under this assumption, he proved that no dispersion-free states where all observables have a definite value, could exist, thereby ruling out a hidden variable explanation for quantum statistics. For decades, this proof was widely accepted as the final word on the matter, a mathematical bulwark against any classical-style revision of quantum theory. However, the argument contained a subtle vulnerability. In 1935, the philosopher and mathematician Gret Hermann identified a flaw in von Neumann's reasoning, pointing out that his assumption about the additivity of expectation values for incompatible observables was a physical requirement, with little justification in a hidden variable context. Her critique, published in an obscure journal, went largely unnoticed for many years. It was only in 1966 that John Bell, while re-examining the question, independently rediscovered the weakness of von Neumann's assumption. Bell formulated his work differently. He derived an inequality, a statistical test based on assumptions of locality and realism, which any local hidden variable theory must satisfy. He then showed that the predictions of quantum mechanics violate this inequality. Subsequent experiments, notably by Alain Aspect and his successors, have overwhelmingly confirmed the predictions of quantum mechanics, thereby ruling out local hidden variable theories. This later development reframed von Neumann's contribution. His proof was correct given its premises. It stands as a valid argument against a specific, albeit overly restrictive, class of hidden variable theories. The episode illustrates a fascinating dynamic in scientific progress, where even a flawed impossibility proof can profoundly shape the discourse for decades and ultimately provoke the very work that clarifies its limitations, leading to a deeper and more nuanced understanding of reality's strange quantum fabric. The influence of mathematical foundations of quantum mechanics was immediate and enduring. It provided a lingua franca for a generation of physicists, enabling them to communicate and build upon the theory with unprecedented clarity and confidence. The abstract framework, initially intimidating to some, became the standard pedagogy, the very way quantum mechanics is taught and understood. Figures like Eugene Wigner, von Neumann's friend and brother-in-law, extended the use of group theory within the Hilbert space formalism to spectacular effect, classifying particle states and uncovering deep symmetries of nature. The rigor of the work paved the way for the even more mathematically demanding developments of quantum field theory and the standard model of particle physics. Its concepts are woven into the very fabric of condensed matter physics, quantum optics, and quantum chemistry. The legacy extends far beyond physics. The field of operator algebras, a major branch of modern mathematics, grew directly out of von Neumann's work on the rings of operators studied for quantum mechanics, later known as von Neumann algebra. In conclusion, John von Neumann's 1933 treatise was far more than a textbook or a synthesis. It was an act of profound intellectual legislation, establishing the constitutional law of the quantum realm, drawing upon the formalist program of David Hilbert and the raw physical insights of the theory's pioneers. He constructed a mathematical superstructure of such elegance and power that it has remained the bedrock of the field for nearly a century. He took a theory born from puzzling experimental results and brilliant but disparate formalisms and gave it a unified, axiomatic, and enduring form, while the book formalized the perplexing measurement problem and offered a flawed but highly influential argument against hidden variables. Its central achievement was the establishment of the Hilbert space formalism. This framework, complete with its state vectors, operators, and the versatile density matrix, gave physics the language to explore the deepest aspects of the quantum world. The work stands as a testament to the power of pure mathematics to bring order to the chaos of physical discovery and to provide a lasting structure within which the most profound questions about the nature of reality can be asked, even if the answers remain elusive.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.